Well, hello, and welcome to Doc Onco's Physics. Keith Onco here. Today what we're going to be looking at is the magnetic force on a positive charge that is entering into a magnetic field. We want to see two things. One, what the magnitude of the magnetic force is going to be, and then secondly, and probably even more importantly, what's the path going to look like once that positive charge hits that magnetic field? What's it going to do? Well, first, let's take a positive charge. Let's take a positive charge down here. Okay, and so we have a positive charge, and let's say our positive charge has a value of 5 times 10 to the minus 17th coulomb. So it's a pretty small charge. And it's going to be going up on the page into our magnetic field. And we want to see what the impact of the magnetic field is going to be on that positive charge. We'll say that it's moving with a velocity of 5 times 10 to the 5th meters per second, and that the magnetic field strength of our field coming out of the page is going to be, let's make it 50 times 10 to the minus 5th Tesla. Okay, so it's about 10 times stronger than the magnetic field strength of the Earth. So these are the values. These are the values for B and Q and V that we're going to have. And we know that for a positive charge or any charge that's traveling into a magnetic field, there's going to be a force on that. And the force is going to be dictated by this equation. The force, the magnetic force on the charge, is going to equal to be Q, the charge, times the velocity of the charge, times the magnetic field strength, times the sine of the angle between the magnetic field vector and the velocity vector. If that's perpendicular, then theta becomes 90, and the sine of theta just becomes 1, and that simplifies our equation. So we can easily come up with the magnitude of the force, right? So the force is just going to be Q, 5 times 10 to the minus 17th coulombs. I'll leave the units off for right now. All right, times V, 5 times 10 to the 5th meters per second, times B, 50 times 10 to the minus 5th, that's a 10 there, Tesla. Okay, and so when we do the calculations, we come up with a value for the force, which happens to be 1.25 times 10 to the negative 14th newtons. So that's what's going to be the force on our charge. Now, what is the shape of the path going to look like once our charge hits the field? Well, this is where we really need to use the right-hand rule. Okay, and so the way we're going to use the right-hand rule is, again, we're going to have to take our hand, all right, my fingertips, all right, and excuse me for pointing my my hand in front of my face, but it's the only way you're going to be able to see this. My fingertips are going to point in the direction of the velocity. Well, in this case, that's up on the page. Okay, my palm is going to need to point in the direction of the magnetic field. Well, in that case, it's out of the page. So I've got to turn my hand like this. So my fingertips still continue to point in the direction of the velocity. My palm pointing out of the page in the direction of the magnetic field. And my thumb, hopefully you can see this, is pointing to my right. Okay, so when the charge hits this magnetic field, there's going to be a force on it to the right. So what's that going to do to the velocity vector? Well, it's going to provide an acceleration of that positive charge, and now our velocity vector is going to look like that. It's going to go off to the northeast, if you will. It's going to go off at an angle. Well, now I have a new velocity vector. I'm still going to have a force on my positive charge because I'm still in this magnetic field. So now I'm going to have to take my right-hand rule again. Magnetic field is still coming out of the page, so palm is still pointing up. But now my velocity vector, right, is pointing at an angle. Which way does my thumb point? Also at an angle. And so the new force is going to be pushing that way. What's that going to do to the velocity? Well, it's going to change it again, right? And if we keep doing this, what we're going to find is that the velocity vector is going to continue to change so that our proton, or our positive charge here, is going to go in a clockwise circular path. All right? It's going to go in a clockwise circular path as long as it's in the magnetic field. Okay? This is used in some various different kinds of equipment. One of those types of equipment is the mass spectrometer. A mass spectrometer basically puts a charge onto a molecule or a very small object, shoots it into a magnetic field, and tests to see what the radius of curvature is for the object. And based on the radius of curvature, it can figure out what the mass of the particle is. And by knowing the mass of the particle, we can figure out what the makeup of the particle is. So we have a force over here on the left-hand side, QVB, and it turned out to be 1.25 times 10 to the negative 14th newtons. Okay? So what if we'd like to know what the actual radius of curvature is for this particle? Well, I need to know one more thing. I need to know the mass of the particle. So let's say the mass of our particle, this is a positively charged particle. It's about 10 times the charge of a proton. No, it's more than that actually. It's about 100 times the charge of a proton. So we're going to say it's about 100 times the mass of a proton. So it's going to be 1.62 times 10 to the, we'll make it the 25th kilograms. So that's going to be the mass of our object. Now remember that anything that's going in a circular path from way back in circular motion has to obey, right? If it's going in a circular path, there's some centripetal force acting on it, and it has to obey this equation, mv squared divided by r. The centripetal force is going to equal the mass of the object times its tangential velocity squared divided by the radius. Okay, has to happen. If the object is going in a circular path, this rule, this law, must apply. All right, well, we have a force. We know what the centripetal force is. It's due to QVB, and it's 1.25 times 10 to the minus 14th newtons. So that's going to equal, in this case, the mass of our object, 1.62 times 10 to the minus 25th kilograms. There should be a minus over here. Times the velocity squared. Well, the velocity is 5 times 10 to the 5th meters per second squared, all divided by r, because we're trying to figure out what the radius is. So when we plug this all into our calculator, let's see what we get. So when we do the math, r turns out to be a fairly large number, and it's 3.24 meters. All right, that's a pretty big radius. All right, so it's not terribly realistic, but again, I just made up the numbers, so that's okay. But anyway, this is how we analyze a charge that's going into a magnetic field. It's going to go in a curved path. It's going to have a force on it. One last thing though, what would happen if this charge here, right, instead of being positive is negative? What's going to be the direction of our path? What's the path going to look like? Well, it's still going to be a curved path, but instead of going in a clockwise direction, it's going to go in a counterclockwise direction, because the force is going to be opposite for a negatively charged particle than it is for a positive charged particle. Hope that helps. We'll see you next time.